Welcome to the SciPhi Show, where we talk science and philosophy with two of my favourite atheist thinkers, Alex Malpass and Dan Linford. And now, recently, my colleagues and I did the largest ever survey of physicists on controversies within the field. And one of the questions that came up was fine-tuning. We're often told that we need to choose between a multiverse or God. And what our survey revealed is that physicists mostly choose neither. And also there was the Phil Paper survey of philosophers, and that showed the very same thing. So after 50 years or more of the modern fine-tuning argument, it has failed to convince physicists or philosophers. But why? Well, today, Dan Linford is going to present his case about fine-tuning, and there's very few people on the planet that know both the physics and the philosophy as well as Dan. So I'm super excited about this. He's going to go over the problems, the different notions of fine-tuning that physicists actually use. Now, this is a little bit of a follow-up to a short debate that he had with fine-tuning dependent Philip Goff. That's only 20 minutes. I'll put a link in the description if you want to see the entire thing. But if you didn't see it, don't worry, as we're going to be a much deeper dive here. So why don't you take it away, Dan?
All right. So as Phil was saying, this is my reply to Philip Goff's fine-tuning argument. And the version of the argument that I'm replying to is the version that appears in the little online exchange that I had with Philip. I will reference his book as well, because there's some slight differences between what he says in his book and what he said in our online exchange. And actually turns out that some of the problems that I identified in our online exchange were issues that don't appear for the presentation in his book. So his presentation in his book is a little bit better than the one that was from our online exchange. Nonetheless, I think there's still some problems there as well. All right, so here's the context that so Philip Goff and Stephen Kirshner, they had a debate on a channel called The Repugnant Conclusion, and then my exchange with Philip happened in the question and answer period. I actually took up 20 minutes of that Q&A, which is Philip and I going back and forth. One thing I want to mention about this is that I don't know that my intentions really came across. So things became a little bit heated between him and I to some extent. That's my fault. I'll mention later on some ways that I think it's my fault in particular. But I did intend at least some of my comments to be constructive, and I don't think Philip really took them that way. I think I also, at some points, mixed up the terms bare value and quantum corrections. I think I mixed those terms up in some of the comments that I've left in various places in the comment section on the video. But anyway, one of the things I want to do today is to clarify my view, elaborate my view, and correct some of my mistakes that I made in that interaction and following it. So what is the argument that he puts forward? In his presentation, he makes the case that fine-tuning supports theism over naturalism. He thinks that this is true relative to some evidence. The evidence that he uses is that there are values of certain constants that fall in a narrow range, compatible that the values of certain constants falling in a narrow range compatible with the universe containing significant value. And by significant value, he means, among other things, that life exists, right? So in other words, that of all the different ways the universe could be, there's a very narrow range of ways that the universe could be that are compatible with life's existence. So he also has this principle he wants to make use of called the likelihood principle. According to this principle, evidence E supports one hypothesis H1 more than it supports hypothesis H2 if and only if the probability of E given H1 is greater than the probability of, this should say, E given H2. Now, what's important about one of the things that's important to understand here is that when we're looking at this kind of relationship, what we're really saying is that H1 predicts E better than H2 predicts E, right? So one of the ways to think about these probabilities is that this is a comparison in terms of how well either hypothesis predicts E, right? In this case, E is evidence at the top of the slide. All right, what are the two hypotheses that we're comparing? Well, the two hypotheses that Philip compares, because he says that theism is a morally good being created the universe, and he tells us that naturalism is the hypothesis that considerations of value play no role in fundamental causal habits. Right, so you might have expected naturalism to be, for example, the hypothesis that nature is all that exists. That's not quite what Philip says here. He wants to define naturalism as saying that considerations of value play no role in fundamental causal happenings. Fine, I'm happy to have that be the definition of naturalism for our purposes. And then the question is, is it really true that we can support theism over naturalism, given both this evidence and this likelihood principle? Is this really a good argument for theism over naturalism? Well, I've got three concerns that I raised, and really this is two concerns, and then there's one closer related issue. So the first concern is that Philip's treatment of probability is missing some important premises. This is what I intended as constructive criticism. But if you watch the exchange here became a bit heated. He accuses me of being pedantic. I think that this is, to a large degree, maybe completely my fault, that I didn't approach Philip in a way that made it obvious that I was attempting to provide constructive criticism. But in any case, one of the things I do want to cover today is what needs to be filled in his argument, and then some of the ways that the likelihood principle can be misleading. And in fact, that will
Dan,
also, yeah.
I just want to defend you a little bit here, because I watched the debate and I did feel that it wasn't entirely your fault. Like, I think he made some mistakes and you corrected him, and he took it, not in the best spirit. Let's put it that way.
Yeah.
So people can watch it and decide for themselves.
Yeah, I think that's what's best. Tell us in the comments what you think, whether it comes across that I was trying to be constructive, or if Philip was being maybe overly defensive, or what was going on. You can let us know. But most of what I want to cover, as far as this first point is concerned, is just to bring the audience in on what's going on in the discussion. The second point here, so Philip's analysis commits the naturalist to a specific physical hypothesis the naturalist doesn't need to commit to. So if we go back to the previous slide, in order to apply this likelihood principle, right, we're going to need to be able to say something about how well either theism or naturalism predicts the evidence. And I make the claim that you can pull out the relevant statement about likelihoods only if you build into naturalism some sort of physical hypothesis. And if you just look at the definition of naturalism here, there's no physical hypothesis at all that's built into the definition of naturalism. Right, so Philip's analysis commits the naturalist to a specific physical hypothesis that the naturalist doesn't need to commit to. And then there's a closely related issue that has to do with the meaning of the phrase fine-tuning. Philip and I previously discussed that on the SciPhi Show, but I wanted to cover it here in a little more depth and unpack a bit more about what's going on there. And in fact, that's what we'll turn to first, is to that terminological dispute. I'll call it the two senses dispute. So I claim that there are two senses of the phrase fine-tuning. One of them I call the philosopher sense, and I call the other the physicist sense. I call them that because I associate one of them with philosophers and the other with physicists, but I don't really want to make the sociological claim that the term is used exclusively in one way in one community and used exclusively in another way in another community. In fact, I was recently reading Luke Barnes's book, the one he co-wrote with Grant Lewis.
Fortunate Universe.
That's right. And in fact, in that book, they use the phrase fine-tuning in both senses. So you can certainly find physicists who use the philosopher's sense and vice versa. But I do want to point out that there are these two senses. Philip claims that the physicist sense, what I call the physicist sense, is irrelevant for the fine-tuning argument. I claim, in contrast, that we should reformulate the fine-tuning argument in terms of the physicist sense, and that when we do so, it makes the situation with respect to the argument look a bit different, and sort of highlight some of the objections that you can pull out for the fine-tuning argument. So what is the philosopher's sense? Well, here's a quote from a now famous paper, at least among philosophers, by John Hawthorne and Yoav Isaacs from 2018. So they say the laws of physics are unexpectedly inhospitable to life. The central notion here is that the universe being fine-tuned for some property. The property of anything you like, containing life, croquet, containing either life before the year 2000, croquet after the year 2000, etc. And what I really want to pull out here is that when we talk about fine-tuning for life in the philosopher's sense, we're talking about a property of the universe being some way, namely the universe being fine-tuned for some property, right? In this case, for life. So philosophers often, not always, take for granted that physicists have somehow discovered this fact about the universe. So the universe has this property of being fine-tuned. And that's how Philip describes fine-tuning in his book, Why the Purpose of the Universe. It's his very recent book. So for example, I just sort of took a random example of his use of the term phrase fine-tuning from that book. He says, we wouldn't be here if the universe was not fine-tuned. You can find that in page 36. Right? So in that sentence, it's the universe that has this property of being fine-tuned. In contrast, in the physicist sense, it's not the universe that's fine-tuned. So here's a sentence from the first paragraph of Simon Friedrich's 2026 article, Fine-Tuning, in the Stanford Encyclopedia of Philosophy. He says, a theory or model is said to be fine-tuned when it reproduces observed phenomena only if its parameters take values within an extremely narrow range among those that the theory in principle allows. Right? In this case, the thing to which the phrase fine-tuning applies is not the universe, but a theory or model. This is going to be a feature possessed by some theories where various free parameters or initial conditions have unnatural or improbable values. Right? So somehow we recognize that the free parameters or initial conditions within a particular theory have improbable values, and then that's the feature that makes that theory fine-tuned. This is taken to be a theoretical vice. Why is it a theoretical vice? Well, it's a theoretical vice because if if we find that this is the case for some theory, then that's some reason for thinking that the theory is improbable. Now, in fact, you don't need to just take my word for it or Friedrich's. As I was saying before, Grant Lewis and Luke Barnes use the phrase in the way that I'd like. And what I realized only very recently was that they describe it as what the physicist means by fine-tuned. So this is two quotes from their book. Similarly suspicious are theories that need very precise values of free parameters in order to explain the data. And they go on to say, this is what the physicist means by fine-tuned. Suspiciously precise assumption. Precision is great in our data, but not in our assumptions. And here is another quote from Luke Barnes. This is from a 2018 paper. This is a great paper, by the way. I highly recommend people read this paper. And in fact, a lot of what I'm going to be talking about today is just contained in these two paragraphs. We'll get to this later, what's at the top, what I call the probability recipe. And this ratio, in fact, will play an important role later on. But right now, we're just talking about fine-tuning of the physicist's sense. And notice what he says here. He says, this is what a physicist means by fine-tuned. Fine-tuned are unnatural theories, right? So theories are the things that are fine-tuned. And they're fine-tuned when they have very small likelihoods. And the more fine-tuned, the smaller the likelihood. And in fact, it presents a good reason to examine our background assumptions and search for an alternative theory, perhaps one whose free parameters are not as fine-tuned, or which the quantity alpha is not a free parameter at all. Right? So based on a theory that's fine-tuned in the physicist sense, what you should be looking for is a different theory that's not fine-tuned, as opposed to saying that the universe has this feature of being fine-tuned and that we know that the universe has that feature. So this invites us to reframe the debate with respect to the fine-tuning argument, right? If fine-tuning is a theoretical vice, then what we want is a successor that's less fine-tuned than our current theories. And in fact, you can sort of see the competition between the two hypotheses most often in debate with one another in the fine-tuning argument as ways of thinking about this. So there's usually people are talking about the multiverse and about theism. Both of those, under this construal, would be theories that are less fine-tuned than current theories. And so the reason to accept either one of them would be precisely because they are purportedly less fine-tuned. Later, we're going to be talking about the cosmological constant as a particular example of a parameter that might be fine-tuned. And there are some less familiar examples of theories that attempt to remove fine-tuning with respect to the cosmological constant. So I've listed them out here. So some of them include massive gravity theories, unimodular gravity theories, gravitational ether. This is I don't know if he originally put it forward, but at least he's published on it that Nayef Shorty, who's a friend of this channel, has written about gravitational ether theories, which purport to give an account of the cosmological constant. There's also higher dimensional theories.
Well, we have a whole chapter about that theory in our book.
About gravitational ether, yes.
Yeah.
Good, yeah. So if you want to read more about the gravitational ether proposal, then that's in the book by Phil and Nayash. And I'm not claiming here that any one of these four, really this is four families of hypotheses, and I'm not claiming that any one of these four really succeeds in getting rid of fine-tuning. They actually are less fine-tuned than our current theories. What I am saying is that the way that physicists are thinking about the situation is that a reason you might prefer any one of these is if it succeeded in being less fine-tuned than our current theories about the cosmological constant. All right, so let's break for a few minutes to chat about what I've covered so far.
Well, I want to just add one other proposal but to me, it's not just another proposal, but it's something that's quite fundamental. And that is, when physicists have a problem, they come up with potential solutions, and you can chat about how plausible they are, and that's a legitimate conversation to have. But ultimately, we want them to make predictions. So when you come up with a theory like unimodular gravity or whatever, then ultimately we want to say, okay, what are the predictions of this theory? So one that I think has got very little attention but deserves more is a theory of quantum gravity called causal sets. Because causal sets says that we can actually explain that, like, the small value of the cosmological constant is often cited as the most extreme case of fine-tuning. Some people say it's the entropy, but I think the entropy one doesn't work because that one's not fine-tuned for life. So no, not that one. But the cosmological constant is appropriate. And there's this theory of quantum gravity, and it says there should be sort of quantum fluctuations in space-time. So there's like atoms of space-time, and they have these fluctuations. And the fluctuations go, if I remember rightly, it's something like 1 over the square of the volume of the space-time that you observe. So that means that those fluctuations will be very, very, very small. So now we have a natural, if you like, explanation of the cosmological constant. It's not fine-tuned in the physicist sense at all. And but here's the important part. It made a prediction 10 years before the cosmological constant was observed, 1998, the accelerated expansion of the universe. Sorkin made the prediction that we should see it. And to me, that gives, now I still think causal set theory is a very incomplete theory. A lot of work, I think, still needs to be done on it. But it gives it an edge over some other competing ideas like theism that made no predictions at all. And they just sort of, look at the data afterwards.
So I don't know that that's quite fair. So what I would want to say here is that so Weinberg gives this prediction for Weinberg co-authors give a prediction for the value of the cosmological constant based on a multiverse and what's called anthropic selection, that you're going to find yourself in the multiverse where it's most probable to have observers. But actually, I think you can retool Weinberg's calculation as a prediction for what you would expect if you had a deity that was particularly interested in the existence of life. And if I'm right about that, then that would mean that theism does make a prediction for the value of the cosmological constant, and that it's basically the same prediction that Weinberg makes.
Well, I would agree they're both anthropic predictions in the sense, but the difference is Weinberg predicted it before it was observed, and theism didn't. Now, you could say, well, if I make this assumption that God loves life, and then he should make the cosmological constant small. But of course, you could make an opposing argument and say, well, if God loves life, he could have made life with any value for the cosmological constant. He can, why should he love life? Well, it has moral value, but you could make spiritual beings that that would have that moral value they're not alive. It's not life that's, why should we think God loves life? So I
Yeah,
think
that's
as a
right.
matter
You
of
have to.
historical record, causal sets did predict it. The anthropic selection with multiverse did predict it. So Weibo predicted it, Sorkin predicted it, but there was no, I don't know any theists that predicted this. And I think that gives these theories a bit of an edge,
Yeah, I mean, what you'd have to do is you'd have to posit a deity that is particularly interested in biological life. And of course, no one has that.
Yeah. Right.
Or, well, I shouldn't say no one has that. No one has a particularly good reason for justifying that. Arguably, Swinburne thinks he's justified that. Whether he actually has is a different story.
Right.
But anyway, Alex, did you want to...
Yeah, I wanted to just make sure I'm getting the distinction between the physicists and the philosopher's sense. So one difference that I saw between the two of them was on the philosopher's sense, what's fine-tuned is the universe itself, whereas on the physicist's sense, what's fine-tuned is some aspects of a theory.
That's right.
And what the fine-tuning in the philosopher's sense, it's finely tuned for something, say, like Hawthorne and Isaacs were saying, it could be finely tuned for X, could be croquet, could be life or whatever. In the physicist sense, it's not so much that they're fine-tuned. Well, is that grammar even still appropriate, that it's fine-tuned for X, where X is the observable data? Is that even, am I using language then?
No, that's exactly right. So you can do it that way. And in fact, this is more or less what Barnes would encourage us to do. And you can still think about it like this. You can say, well, given a theory, the theory postulates that this parameter could come from this wide range of possible values, and then the values that are consistent with some datum, like that life exists, might be very narrow compared to that total possible range. And then we would say that that theory is fine-tuned, or that the value of this parameter within the theory is fine-tuned, and it's fine-tuned in this particular way with respect to this data. Now, there's a sense in which fine-tuning for something is a little bit misleading, because that sort of suggests some teleology, that it's like for a purpose. And I guess you could talk about that when you're talking about a theory. Like when a physicist is fine-tuning a theory, the physicist might have various purposes, like that they want the theory to agree with our data or something like that. But what we shouldn't think is that this has to involve some kind of like a god or something like that. When physicists are using fine-tuning in the physicist sense, it's the fine-tuners are physicists, right? The people that make theories. And they're the ones that are adjusting parameters in those theories in order to accommodate data.
Right. So, but then I'm kind of wondering about the connection between them, because obviously that makes them sound like they're sort of distinct ideas, completely distinct ideas. One of them's about theories, one of them's about the way that the world is. On the other hand, theories are about the way that the world is. That's the point of theories. And if a theory is true, then then it is what the world is like. So isn't there just some sense in which, like, if, I don't know, our contemporary, like, imagine we just by luck, physics is completely correct now. There's nothing else to add to it. We've got everything completely right. Wouldn't that just mean that the universe is fine-tuned and that the theory is fine-tuned? Wouldn't they overlap in that sense?
Well, they could overlap. They don't need to. And it can always be true that a theory that suffers from some theoretical vice turns out to be correct, right? So, for instance, another kind of theoretical vice is complexity. We prefer simpler theories over more complex ones. Of course, it could always be true that at the end of scientific inquiry, the theory that turns out to be the right one is a really complicated theory. But if you're in the middle of scientific inquiry, like we currently find ourselves, and you are faced with a theory that's really complex, then you're justified in trying to find another theory that's simpler. And so the claim is going to be that when you're in the middle of scientific inquiry, faced with a fine-tuned theory, you're within your rights to try to find a theory that's not fine-tuned. And in fact, what we're going to see later is that the probabilities that people pull out these like absurdly small probabilities for the universe to have life when they're talking about fine-tuning in the philosopher sense. If we reinterpret the debate in terms of the physicist sense, then what's going on there is that those are the probabilities that life would exist given that theory. So given a theory of the cosmological constant, if the probability of life existing is 10 to the negative 90, and then you stop yourself and realize, hey, wait a minute, life exists, then that's good reason to reject that theory, right? Because the probability of that theory being correct is absurdly small. Yeah.
So then it sort of reflects the different activities that the two groups are into, right? Like physicists want to work out what the laws of physics are. Philosophers are not so much interested in that. They kind of just want someone to tell them what the laws of physics are, so that then they can go and philosophize about that. So they there's no point in having an argument that proves something like that God exists, and an input to that argument is that these are the laws of physics. If it's not even clear that they are the laws of physics, like a philosopher doesn't know what to do with that. It's like, can I use this premise or not? Like I need the physicist to tell me which, are these the laws of physics or not? It's all very well for the physicist to say, what that's telling me is that I need to go and do some more physics now. That's great. But from the philosopher's point of view, they're thinking, well, come back to me when you've done that and we've got some reliable laws of physics, and then I'll see if I can prove whether or not God or naturalism is the best fit with it, right? So it seems like it's premature. It's like you haven't finished boiling your egg yet, so don't try and start eating it right now or something.
Yeah.
Does that seem fair?
I think something like that is close to what's going on. To be fair, I mean, I've had a suggestion for a long time for theists, which is that faced with this reframing, what they should say is that, hey, I've got a hypothesis that, according to them, predicts the data, and isn't fine-tuned in the way that some of these other hypotheses is, and then that's a reason to take theism more seriously as a hypothesis, right? So that would be a way that a kind of theist-friendly way of reframing the debate. Of course, whether or not it's really true that theism is less fine-tuned is another issue. As Phil correctly brought out, there's this issue about why I think that God is particularly interested in biological life, particularly because God can really violate the laws of nature and so on. That seems like what we're then stuck doing is fine-tuning God's motivational structure or psychology or something like that. Seeing fine-tuning as a theoretical vice, we then want to know whether or not theism itself is fine-tuned.
There's just one other thing, Dan. I was just thinking, is this a good example to tell me if you think I've got this right? So there's another theory of quantum gravity called loop quantum gravity, and they know. I mean, physicists know that there's this formula for calculating the entropy of a black hole. It's called the Becker-Hawking formula. So one hope for a theory of quantum gravity is to reproduce that formula. And in loop quantum gravity, they showed they can do that. But there's this free parameter in the theory. It's called the Barbero-Emmerich parameter. So they have to sort of pluck that formula, if you like, out the air to make it fit. And then they get the formula right for Becker-Hawking entropy. To me, that looks like there doesn't seem to be much to do with life there. It's just about, can we get this theory to replicate what we think our physics already tells us? And so there we see physicists fine-tuning a theory that literally has got nothing to do with whether life exists or the probabilities for life. And then what's interesting is that, well, they say, okay, yeah, we have to fine-tune that parameter, but that parameter turns up elsewhere. So when we do our cosmology, Big Bang cosmology, and then we make measurements of the cosmic microwave background, we can constrain what the value of this parameter is. And now then the theory becomes less fine-tuned because you've constrained the value of that parameter. So it wasn't something that you could just put anything you like in. Is that a reasonable way to think about it?
Yeah, it sounds like. I mean, I haven't studied that particular case, but that's it does sound like what I'm talking about. I think it's important to note that when physicists talk about fine-tuning as this theoretical vice, one way that we can think about it is in terms of these issues that have to do with life. But in fact, physicists often use the phrase fine-tuning in this sense in cases that have nothing at all to do with life. The one of the things that Alex said when he was talking was that it seems like these are two logically distinct notions, and they are two logically distinct notions. That is the fine-tuning in the physicist sense and fine-tuning in the philosopher sense. One of the ways to notice that they're really distinct is that there are cases where we would want to use fine-tuning in the physicist sense, but we wouldn't want to talk about the issues that come up when philosophers usually talk about fine-tuning. Nonetheless, in the various cases where people present the fine-tuning argument, it turns out that these things exactly coincide. And not only that, but not only do they often coincide, if you look at some very sophisticated presentations of the fine-tuning argument, like Luke Barnes's, he just straight up uses the physicist sense, right? So when he's talking about his version of the fine-tuning argument, this just is the sense that he's intending.
Cool. All right. Should we press on then to the next part of the presentation?
Yes. Yeah, absolutely. All right. So I brought up before that there were the two sets of concerns. One had to do with probability, and the other had to do with the background physical hypothesis. Let's talk about those probability concerns. So Philip claims to be giving a Bayesian argument. In my exchange with him, I said that his case was incomplete and that what he seemed to be giving really turned out to be something more like a likelihoodist argument. Nonetheless, I think that and I think, in our exchange back and forth, we sort of covered this. There is a way to modify the argument that Philip gives to make it into a Bayesian argument. It's sort of obvious to philosophers who are familiar with this material how to exactly do that. But I did want to show the audience what's involved here and some things that someone could get tripped up on. Not to say that Philip would necessarily get tripped up on those points. And, I mean this to be friendly. I mean this as a way to complete Philip's argument, to complete the presentation that he gave in his discussion of it. And so this, if you'd like, isn't necessarily an objection per se to his argument, as opposed to just a completion of his argument. So first of all, what is Bayesianism? So Bayesianism is a philosophical view that says a number of different things, but these are the three most important. First of all, it says that ideal reasoning under the condition of uncertainty should be modeled using the probability calculus. And second, rational beliefs are assigned what we call credences. And then we think about those credences, we model them as probabilities, and those probabilities are going to represent a relative degree of confidence in a hypothesis or a belief. When we update our credence in light of new evidence, we should update according to Bayes' rule. So Bayes' rule is down here at the bottom. There's a very closely related theorem in the probability calculus called Bayes' theorem, but the Bayesian takes Bayes' theorem and updates it to or raises the stakes of it to the level of a rule or a principle, what they call Bayes' rule. So it says that the posterior probability, that is the probability of the hypothesis given the evidence, is equal to the prior probability, the probability of the hypothesis by itself, multiplied by the probability of E given H. That's what we call the likelihood. Basically, that's the degree to which the hypothesis predicts H. And then you take that product and you divide it by the probability of the evidence. Now, what is it that makes this different from Bayes' theorem? What makes it different from Bayes' theorem is that according to the Bayesian, when you're presented with new evidence, you should use this formula to update the probabilities that you assign to any given hypothesis in light of that new evidence. That's what distinguishes the Bayesian from other views that might think about credences in terms of probabilities. In contrast, there's a view called likelihoodism. According to the likelihoodist, we can't reasonably assign probabilistic credences to all of our beliefs. In many cases, we can't agree on prior probabilities, for example. So if you look back at Bayes' rule, there was this probability of H sitting here. That's the prior probability. The likelihoodist points out that any assignment of those prior probabilities is usually going to be controversial. And so in order to get around that controversy, they say we should be thinking basically solely in terms of these likelihoods, the probability of E given H. And then instead of thinking about whether one hypothesis is more probable than another, what they want to talk about is whether one hypothesis is favored over another. So hypothesis H1 is going to be favored over H2 when H1 predicts the data better than H2. So the probability of E given H1 is greater than the probability of E given H2. Now, there's a few things that are really important here. One of them is that just because H1 is favored over H2, that doesn't entail that H1 is more probable. In fact, the exact opposite could be true. It could be that E favors H1 over H2. Nonetheless, H2 is more probable than H1. We'll see an example in a moment of that. I also want to point out, and I'll show an example of this as well, that favoring is not the same thing as having evidence, let alone having strong evidence. So you can fulfill this formula here, even though E is not evidence for either hypothesis. All right, well, can a bad hypothesis be favored over a good hypothesis? Here, what I have in mind is a situation where we have a hypothesis whose probability is very low, and yet it's favored over some other hypothesis whose probability is very high. So this is going to be a way that the Bayesian thinks that there's a defect in likelihoodism. And since Philip is a Bayesian trying to present a Bayesian argument, you should agree that this is a defect in likelihoodism. Of course, a likelihoodist wouldn't necessarily think that because there's a sense in which this is sort of question begging against the likelihoodist. But in any case, since both of us are Bayesians, we're thinking about this as a defect from the Bayesian perspective in likelihoodism. So what is the example? Well, let's suppose that I hear a noise in my attic. Now, here's one hypothesis. It's the hypothesis that there are gremlins who produce precisely that noise. I cook up this hypothesis that I call G in order to predict precisely that noise. In that case, the probability of that noise given G is just 1. It's as probable as any hypothesis could be. Here's an alternative hypothesis. It's the hypothesis that there are rats in my attic. Now, the hypothesis that there are rats in my attic is more probable relative to our background knowledge. And we know that there are such things as rats. We're pretty sure that there are not such things as gremlins. So we're pretty sure that if I hear a noise in my attic, rats are good candidates as to the cause and gremlins are a bad candidate. So even though the probability of noise given the gremlin hypothesis is more probable than the probability of the noise given the rats, nonetheless, the probability of the gremlins given the noise is less than the probability of the rats given the noise, right? So even though the gremlins predict the noise, nonetheless, we should believe the rats hypothesis over the gremlins hypothesis. All right.
And just to sum up, yeah. Dan, just to sum up, the reason that the gremlin hypothesis is less probable is because we give that a low prior. And is that basically it?
Yeah, no, that's right. Yeah, so it's one of the important things here is that I said this is all all relative to our background knowledge. Our background knowledge is everything else we know about the world. So everything else we know about the world includes that there are such things as rats, probably not such things as gremlins. We give the gremlin hypothesis a low prior. We give the rat hypothesis a fairly substantial prior. And so we end up thinking that the rat hypothesis is probable and the gremlin hypothesis is improbable. The fact that we heard a noise that these gremlins are postulated to produce doesn't really make a difference with respect to that analysis. All right. Well, it also turns out that when E favors H1 over H2, nonetheless, it's possible for E to be evidence against H1. Right? So even though one hypothesis is favored over another, it doesn't follow that that evidence is evidence for that hypothesis. I work on an example down below. I'm not going to work through the details, but people can freeze this and take a look at it. What's really important is the definition we're using here for evidence. So we're using what's called the positive relevance theory of evidence, and that states that statement E reports evidence for H just in case the probability of H given E is greater than the probability of H. What that means is that E raises the probability of H. So if you have some statement that increases the probability of our hypothesis, then it's evidence for that hypothesis. And it turns out that even when one hypothesis is favored over another, that the evidence that does the favoring could actually lower the probability probability of the hypothesis that's favored. Now, there's something that's very closely related. It turns out that favoring is related to evidence. It's just that in a case like this one, we're thinking about two hypotheses where one hypothesis is not the negation of the other. So if you look carefully at the math I did here, I actually considered three hypotheses, H1, H2, and H3. Since I'm considering three hypotheses, H1 is not the negation of H2. But if we consider a hypothesis in its negation, in that case, E is evidence for H if and only if E favors H over its negation, right? So when we think about a hypothesis and its negation, in that case, we can actually think about a relationship between favoring and evidence. One proviso here is that this formula that I provided follows from Bayes' theorem, but only as long as we assume the prior probability of H is not 0 or 1, so it's in between 0 and 1, and the probability of E, the probability of the evidence, is at least greater than 0. Right, and then I put this extra word of caution down here that we just covered, that a closely related statement where we have H1 and H2 instead of H and IH is not true. Now, in the debate, the likelihood principle that Philip gives, it's this one down here. This is from that screenshot I showed earlier of his slide in the debate. Here's how he says the likelihood principle during the debate. He says that evidence E supports H1 more than it supports H2, if and only if the probability E given H1 is greater than the probability of E given H2. Now, one way that you could take this is that this is just a definition of the term supports. If this is just supposed to be a definition, then one thing to notice is that the term supports is being used here in a way that's a bit awkward, because it doesn't mean that E is evidence for H1. It's not evidence supporting H1. On the other hand, if you don't mean it as a definition, and you take support to mean evidence for a hypothesis, then this likelihood principle that he gave in the debate is just not true. However, in his book on pages 26 and 35, he gives a better principle. So at top, you can see he says, we can sum this up with the general principle over here. Our principle is just derived from Bayes' theorem, the likelihood principle. If the evidence is more likely assuming the theory is true than assuming the theory is false, then the evidence supports the theory. Well, that's just what we had on the previous slide, right? That was, we said what the relationship was between evidence according to the relevance theory and this the statement about likelihoods. So this statement here at top, yes, it does follow from Bayes' theorem, so long as you also assume the relevance theory of evidence. In the middle here, this is from page 35 of his book. This is what he calls the comparative likelihood principle. This is a bit closer to what he had in his slide. He says, if the evidence is more likely assuming theory A is true than it is assuming theory B is true, then the evidence supports theory A over theory B. And again, there's this ambiguity about what the word supports is supposed to mean. Again, if this is a definition, then it's a misleading way to define the term supports. If this is supposed to be something that follows from Bayesianism under a more typical notion of the understanding of the word supports, then it's easy enough to generate counterexamples to the comparative likelihood principle. Right, well, let's fix up Philip's argument. And here is what I claim his argument should have been, and I think it's really what he intended. So the first premise says that the probability of O given H1 is much, much greater, vastly greater, than the probability of O given H2. And here H1 might be theism and H2 might be naturalism. So when we say that the probability of the evidence from earlier, about those constants have to be in that narrow range, if that makes the observation of life's existence very, very improbable, like 10 to the negative 90, like we'll see later, then that would mean that basically any value you want to have for the probability of O given H1 would make it vastly greater than the probability of O given naturalism. The second premise is that the ratio of the priors, so in his argument, be the ratio of the probability of theism to the probability of naturalism is not too low. And Philip seems to think that he doesn't really have to say what either of these two prior probabilities are. All he needs is that you don't set this ratio like absurdly, preposterously low. He discusses that on pages 37 to 39 of his recent book. Third premise is just Bayes' theorem, basically. This third premise allows us to convert these two premises 1 and 2, into a statement about posterior probabilities. So if you've got 1 through 3, then you can conclude that the probability of theism given your data is greater than the probability of naturalism given your data. And that would be a reason for preferring theism over naturalism because it is a higher posterior probability. But, again, this word of caution, that this is not a reason to think that theism is probable. You're not able to conclude that, or that the observation that you have is evidence for theism, because as we've covered, it's possible to fulfill the likelihood principle, or the formula from the likelihood principle, without actually having evidence for your hypothesis.
So, just for the sake of getting the terms clear, just give me a clear, straightforward distinction between a Bayesian and a likelihoodist, because you make it sound like they are competing factions, like the Bayesians and the likelihoodists sort of hate each other and, throw stones at each other or something. So what is their disagreement? What's the main difference between the two camps?
So the Bayesian thinks that we can assign credences to all of our hypotheses or all of our beliefs. The likelihoodist thinks that we can't do that, and that we shouldn't be thinking about these like Bayesian updating procedures. Instead, we should be thinking about in cases where we can't assign prior probabilities, so we can't and then make the move the Bayesian wants to make. We should then be comparing likelihoods. And since the reason I say that Philip offered a likelihoodist argument was not that he intended to defend likelihoodism, but rather that he what he ends up doing is talking about how the likelihoods compare, which is a move that a likelihoodist might make, instead of filling out the complete Bayesian version of the argument, where you also bring in priors and then try to make some statement about posterior probabilities.
And I mean, is it the sort of thing sorry, just one little follow-up on that. It's just that could you be a Bayesian? I mean, presumably Bayesians can use the likelihood principle, and it's part, as Philip pointed out, it's part of the Bayesian probability calculus. So, does it automatically tell you, just because you see someone making a likelihoodist comparison, that they're not a Bayesian, or that they don't mean it in talking as a Bayesian or something?
Yeah, I didn't intend to say something like that. Yeah. So everyone has the version of the likelihood principle that actually follows from Bayes' theorem, the one where you compare H and not H, that's everyone has access to that as long as they think that we should be assigning probabilities in the context in question. That's just a standard piece of probability theory. So when I say that he was giving a likelihoodist argument, what I meant was that he was giving the kind of argument that you might have expected a likelihoodist to give, and not that we can identify Philip as a likelihoodist, because I don't think that he is a likelihoodist. I think that he tells us he's a Bayesian. I have no reason to disbelieve him when he says that.
And I mean, just very quickly, I just think that's possibly why he thought you were getting at him, was because he was going, well, look, I can just talk about the likelihood principle. It doesn't mean I'm a likelihoodist. You're trying to pin me as being part of this, group of whatever philosophers, people who take this view. And he didn't mean to come across that. I think maybe I'm misremembering, but it seems to me that's something to do with how he felt you were getting him.
Yeah, but the problem is that the version of the likelihood principle that he gives in the debate, the one where we compare H1 and H2, is one that does not follow from Bayes' theorem.
Right.
So in that case, that's a principle that it seems like the likelihoodists would be attracted to, because they're not talking about priors, and then they need to talk about favoring or supporting or something like that.
Got it.
Whereas the Bayesian would find that objectionable, precisely because what they want to know is whether we really do have evidence for a hypothesis, and not just what the relationship might be between the likelihoods.
Dan, can I ask you to steelman the likelihoodist position, and with respect to the gremlins example? So obviously the Bayesian just says, well, we've got really low priors for the gremlins. So I'm going to not believe that the gremlins are causing the noise in my attic. What would a likelihoodist say? Presumably they wouldn't say, well, I take the gremlins to be just as likely as the rats. I mean,
Yeah.
I mean, who's going to say that? And what is their basis? If they are going to say, yeah, the rats is more likely, what is the basis if we don't allow prior?
Yeah, good. So there's a philosopher of science named Elliot Sober. He's one of my favorite philosophers of science, and he is a likelihoodist. So there are quite good people that are likelihoodists. And there's a book he wrote, a classic book called Evidence and Devolution. And in that book, he gives a likelihoodist formulation of design arguments. And he covers this kind of objection involving the gremlins and so on. What he would say is that it's not enough for a hypothesis just to be preferred in terms of the likelihoods. After all, you can always cook up a hypothesis that predicts exactly the data that you want. That's the point of the gremlin example. It also has to be that the hypothesis that you're considering fulfills other sorts of theoretical virtues. Now, there's some debate among likelihoodists about what exactly that extra theoretical virtue might be. Vaguely, you might think that it shouldn't be, for example, ad hoc. Basically, this means that it shouldn't be cooked up just to explain the data that you have. But there's quite technical considerations that likelihoodist philosophers have about what this extra condition is going to do, and it's precisely the condition that's supposed to rule out these kinds of gremlin cases. The Bayesian, looking at that debate, would say, "Oh, I have an extra condition, namely my thing about priors." Likelihoodists, looking at the gremlin example, would say, well, I'm not going to bring in priors, but I'm going to bring in other theoretical virtues that I want hypotheses to fulfill. And then I'm going to claim that it's a hypothesis that it's not enough for hypothesis to be favored over other hypotheses. We also need it to fulfill these additional theoretical virtues.
And is it good practice when you construct your Bayesian probability? Like, there's another type of probability called frequentism, right, where you just sort of count what's observed and do your probabilities that way. So, like, imagine I have a coin, and I say, okay, it could come out heads, could come out tails, or it could come out on its side, could land on its side. But I'm going to throw it 1,000 times. Oh, look, I never see it land on the side, so I'm going to throw that out. We'll just not include that in my probability calculation. Is it good practice to, if you have access to frequentist data, to use that for your prior?
So there's various thoughts you might have about what the relationship is between two things. So let's move back up a moment. There's a classic debate in philosophy of probability between Bayesians and frequentists, where this debate is sort of different from the likelihoodist Bayesian debate we talked about previously. This debate has to do with whether we should think about probabilities as degrees of belief or credences, that's what the Bayesian says, versus whether we should think of probabilities as frequencies with which various events happen. That debate is related, but not precisely the same thing as the thought that there's a distinction between what we call chances and credences. So a credence is your degree of certainty or uncertainty. That it's the credence is the kind of probability that Bayesian believes in. A chance is the kinds of probabilities that physical theories give us. So when we say that, oh, there's a probability for a radioactive nucleus to decay in the next minute, for example, what we're reporting there is a chance. But also when we give weather reports, we're giving, if we say it's 60% chance of rain, that we're giving a chance. In fact, I even use the word chance there. There's a debate about how we should think about what the relationship is between credences and chances. sort of standard view is what's called the principle. This is what David Lewis came up with. Maybe people had this before Lewis, but Lewis is famously associated with it. We've got credences, we've got chances, and we've got David Lewis, who is famously associated with the principle. And what the principle says is that if you're given a chance for something to happen, and you're given no other information, so all we know is the chance, then the credence that you should assign is just equal to the chance. So if I know that the chance of it raining tomorrow is 60%, then my credence in it raining tomorrow should be 60%. That's what the principle tells you. Of course, now if it comes tomorrow and I observe rain, now my credence is 100%. It's now differs from the chance, right? But that's because I have additional information. As far as your question, whether we want the chances to agree with the priors, well, if all that goes into the priors is just my knowledge about the chances, then according to the principle, the prior should be equal to the chance.
Right. So I guess the reason I ask is how. So I understand what Philip Goff and others are arguing is that we try and estimate the probability that God would fine tune the constants, and we try and estimate the probability that they would get there by chance, and we find, well, I don't necessarily know what these numbers are for God, but I know they're not that low. So we're trying to estimate the two probabilities, and what we need is the God one is not anywhere near as low as the naturalism one. But I might say something like, well, I'm going to give God a really, really low credence because, hey, I've observed lots and lots and lots of minds, like trillions of them, or I don't really observe them, but, I know there are trillions of minds. And the number that can change a constant of nature is 0. So, okay, there's always a possibility that there's one that I haven't observed. But given my frequentist data, my credence that there's a mind that can change a constant nature is really, really, really low. So maybe I can be justified in assigning it this crazy low probability. And that seems to me where the difficulty may lie in assigning these prior.
So there's different ways we can present the fine-tuning argument. I've presented it the way that I think Philip wants to understand it. There are some other people like William Lane Craig who presented a slightly different argument. This is a version of the argument that I think comes close to what you're talking about. And it's one that I sort of associate with the intelligent design community. And the way this argument is supposed to go is that the constants could either be due to design, chance, or necessity. And then we're supposed to think that there's good reason to rule out chance and necessity. And so we're left with design. Philip doesn't present the argument that way. And so because he doesn't present it that way, he doesn't commit himself to saying that the constants have the values that they have by chance. But certainly if someone did think about it in those terms, like Craig, I would want to know where these chances are supposed to come from. If they come from a background physical theory, well, then you're going to run into the problems that we'll discuss momentarily. Philip also he doesn't say this in his presentation of the argument, but he too will need to draw probabilities given a background package of physical hypotheses. And so in either case, you run into a kind of objection that I'll be talking about momentarily, but whether or not we should really accept that background package of physical hypotheses. All right, so I told you that the next part we want to talk about was what physical hypotheses naturalism is committed to. Remember that for Goff, naturalism is just a view that fundamental causal reality doesn't select for things that have value, like things like life or something like that. All right, so now in the debate, if I remember correctly, Philip makes this claim. He didn't put this on a slide, but this is the kind of claim that he made there, that the probability of life given naturalism is something like 10 to the negative 120. This number, in order to make this number, you can't just use naturalism. Naturalism doesn't allow you to make this computation. what will allow you to do this computation is a more specific physical theory or hypothesis. We'll see that this isn't quite the right number. One of the corrections I want to make is that, I've given this 10 to the negative 120 number. Various people have done so. It's not really the right number, and I'll show you what the number should be. But even once you have the right number, it's still true that you need a background physical theory more specific than naturalism. But the naturalist, right, so this is what I was saying, the naturalist, qua naturalist, isn't committed to any specific physical theory or hypothesis. So this statement at top here that I've called claim is going to require that our background knowledge includes two statements, or at least something relevantly similar to these two statements. There are ways you could formulate the argument in terms of some other statements, but they're all going to basically end in the same place. So you need a physical hypothesis. In this case, the physical hypothesis is that the vacuum energy calculated from quantum field theory gravitates like a cosmological constant. When I use that term gravitates, it just means that it exerts a gravitational influence, and the kind of gravitational influence it exhibits is the kind of gravitational influence that the cosmological constant, and we'll talk about what that is momentarily, the kind of gravitational influence the cosmological constant exhibits. In addition to the physical...
Dan, just didn't not confuse people. I think we're saying it's a negative gravitational effect, right? It's repulsive.
Yes, that's right. Yeah, so ordinarily the gravity we think of as being attractive. The cosmological constant is a bit odd because it's repulsive. It pushes things apart. And so what we're concerned with is that repulsive term that appears in the in general relativity. We also need a probability assumption. So it's not enough just to postulate some physical hypothesis. That alone is not going to give you anything about probabilities, because a physical hypothesis just by itself doesn't usually tell you whether the parameters, the free parameters that appear in that theory are going to have probable or improbable values. So you need something in addition. You need what I'm calling a probability assumption. All right, well, let's talk about this cosmological constant. So it turns out that the universe is not only expanding, the universe is accelerating. And that this accelerated expansion is due to some mysterious repulsion. That's that cosmological constant we're talking about. This is roughly the same thing as dark energy. Those two terms are often used interchangeably. One initially plausible hypothesis, that's the hypothesis that it's this thing we call the vacuum energy, predicts a value that's 10 to the 120 times too large. And this hypothesis can be saved if we postulate some other effect that almost completely cancels out that 10 to the 120 number. Not completely cancels it out, but very nearly does so. But that cancellation is improbable unless we postulate something like that life must exist, some kind of what I call an anthropic mechanism. By an anthropic mechanism, I just mean some mechanism that ensures the existence of life, whether that's God or multiverse or axiarchism or some other kind of hypothesis. The claim is going to go that this cancellation is very, very improbable unless we have some additional postulate that makes life very likely.
So interestingly, on Philip's definition of naturalism, then there couldn't, any cancellation that was sort of aimed at a value like axiarchism just doesn't count as naturalism because it's aimed towards, because value is involved in the causal comings and goings of the universe then in that case, because right?
Yeah, so, I think that's close to being right, but not quite, because and maybe we need to modify this last bullet point, but if you had like a multiverse plus anthropic selection, then in other words, you have a multiverse, and so overall there's no preference for life, but your observations are going to be biased in terms of seeing life because you couldn't exist in some place where life couldn't exist. And that would be another way of ensuring that the cancellation that you observe is this particular value. And I take it that hypothesis, that multiverse hypothesis, would be a naturalistic hypothesis in this sense.
Right. Yeah, that would be. But axiarchism, which you did mention a moment ago, seems like it's excluded from Philip's definition of naturalism for some reason. Just a reason why I didn't like that definition.
Yeah, no, that's right. I think that this is, and this goes back to something I was mentioning earlier when we were talking about the likelihood principle, which is that instead of considering a hypothesis and its negation, he thinks about two hypotheses where it's possible for neither one of the hypotheses to be true.
Yeah. And I basically, and not to sidetrack, but that's one of my main kind of complaints with the fine-tuning argument in general, is that it's like, okay, well, maybe you're right that a version of naturalism is not expected given this evidence, but that doesn't mean naturalism per se is now like unlikely or something. It just, some version of naturalism where we roll some like cosmic lottery at the beginning to see what the constants are going to be, that type of thing seems okay, fine. Well, I'm happy to just reject that. Doesn't, just like every theist is going to reject some version of theism, and every naturalist is going to reject some version of naturalism, and it doesn't matter. That's fine. Cool with that, So anyway, that's just my grumble. It's a separate thing from what we're talking about.
Actually, I want to just say something about that, because this is kind of, I just want to develop that a little bit. Like, we have cases before where, I mean, let's think of it this way. I often hear from theists, I'm not an atheist because I don't believe the whole world's just random. And I'm like, well, I'm an atheist, but I don't believe the whole world's just random either. It doesn't follow that if you're an atheist, everything is random. So, and the classic example, of course, is, in Darwinian evolution. So if I don't see why the fine-tuning argument is any different to the biological design argument, because ultimately we could cash. Dan, let me finish and then chime in. So we could cash out the biological argument of saying, okay, arrange the genes. If we arrange the genes or genetic information randomly, how much of the probability space will we have that gives you a life-permitting organism? It's probably tiny, right? Very, very few organisms will be life-permitting. So what do we conclude? Do we conclude, well, it must be designed? Or do we conclude the way that came about wasn't through random chance? And then it turns out Darwinian selection is not just random chance. I mean, it has a random component, the mutation, but there's a non-random component, which is selection. So, but generalizing it, you just say naturalism does not equal random chance. And so the fine-tuning argument, which is, well, I'm going to assume that the constants were chosen by random chance. And like, okay, that's not naturalism.
So I think it's important to point out that that Philip actually, so in Philip's book called Why, in the chapter on fine tuning, he actually points out that precisely what you just pointed out about Darwinian evolution, he points out about Darwinian evolution, that the two possibilities are not chance or design, that natural selection gives you an alternative possibility. Of course, he then also goes on to give the fine-tuning arguments. He thinks that there's some important disanalogy between these cases. I did want to acknowledge that in his book, he does say precisely the same thing.
In his book, he does, evolution. But since he published that book, he has now moved to. When he wrote Why, it doesn't make the argument for theism, but since that book came out, he has made the argument for theism. So I think it's on slightly different grounds now. But anyway, I just want to clear up one tiny minor terminology thing that might help people. And this is what I've come across from my discussion with physicists, is that the distinction between dark energy and cosmological constant is that dark energy is a term used to describe whatever is pushing the universe to accelerate in its expansion. And there's no assumption that it has to be a constant. Whereas if you think it's a cosmological constant, then obviously you're committed to it being a constant. But it could change over time, and it could turn negative. And if that were the case, it would still be dark energy, but it wouldn't be a cosmological constant.
Yeah, that's fair enough. That's exactly right. If you had a hypothesis like quintessence, for example, then you're postulating that dark energy is some field that changes over time, and that in our present cosmological epoch, the dark energy looks very constant because it's changing very slowly, and or maybe not changing at all, at least within our present cosmological epoch. And then as far as general relativity is concerned, you would be able to approximate it as a constant. And so it would look like a cosmological constant.
Right. Okay. Shall we push on?
Yes, let's do that. All right. So here is something called the cosmological constant problem. It's what I was describing on the last slide, and I want to include this because this is the description of this problem from the paper that Lewis Barnes and Philip Goff co-authored this and published this earlier this year. So they say, what is this repulsive force? Physicists realized that there was what seemed like an obvious culprit in their equations, namely that dark energy is a manifestation of what is known as the quantum vacuum. How well did the physicists do in predicting the observed energy density of the cosmological constant? The prediction differed from the observed energy density by a huge amount, a factor of 10 to the 120, a 1 followed by 120 zeros. This discrepancy has been referred to as the biggest embarrassment in all of physics. Right. And one thing to notice is that this is a fine-tuning in the sense that we talked about earlier, in the physicist sense, right? We've got a theory where a free parameter in the theory, the cosmological constant, has a very improbable value. All right, well, let's dive more into what exactly that theory is. I don't imagine that many people in the audience will know what this equation is on screen, but it's the Einstein field equation. We're not gonna go through how to solve an equation like this or exactly what these terms mean, but we're gonna look at these terms sort of schematically. So on the left-hand side, this is a bunch of terms that represent the curvature of space-time. And on the right-hand side, I've grouped together a bunch of terms that have to do with the matter and energy in space-time. This final term here, the cosmological constant term, is often put on the other side of the equation. But for our purposes, I wanted to put all the terms that have to do with the matter and energy populating space-time on one side. The first term is just ordinary matter and energy. So this T with the subscript mu nu, that's ordinary matter and energy. The second term, G mu nu times lambda. Lambda is what we call the cosmological constant. And if you had something that was a very slowly changing field, but was not in fact constant, then you could include a term that looked an awful lot like this and be approximated by the same term. Or this could actually just be like a literal constant we were discussing. Now, general relativity tells us about the geometry of space-time, but only as long as we provide some matter and energy to populate space-time. In fact, this is one of the things that Einstein himself disliked about general relativity. Einstein himself felt that general relativity wasn't complete because it didn't include a theory of matter and energy. You have to look outside of the theory to tell you about matter and energy. And then when you have some theory of matter and energy, you can plug it into the Einstein field equation. And then that can tell you about the other side of the equation, where we have the curvature of space-time. And so looking ahead, part of what was going to happen is that we need some theory of matter and energy to tell us about this cosmological constant term. Now, one of the things I want to point out is that even though general relativity doesn't give us a prediction for this cosmological constant term, it doesn't itself include that internally, it does include what I'm going to call an anthropic interval. So an anthropic interval is a range of values that's consistent with the existence of life. So there's a range of cosmological constant values where the universe wouldn't expand too rapidly or collapse too rapidly to allow for life to exist. If the cosmological constant is too big and positive, the universe exponentially rips itself apart. If the cosmological constant is too large in magnitude but negative, too big of a negative number, then the universe will collapse back in on itself, and therefore also prevent any kind of large-scale structure from forming. The interval of values in between, the interval of like moderate cosmological constant values, that's the anthropic interval. But the fact that the theory itself doesn't tell you whether that interval is wide or narrow tells you that the theory itself doesn't make any claims about whether that anthropic interval, whether the theory is fine-tuned. Right? We're going to look for, you need to input something else in order to tell us whether the cosmological constant is fine-tuned. It's not enough just to have an anthropic interval. All right. Well, I told you before that we need some theory of matter and energy in order to give some content to the right-hand side of that equation we're just looking at. Well, our best theory of matter and energy that we at least currently have on offer, it's not actually one specific theory, even despite its name. It's actually a family of theories. It's a theoretical framework, if you will, called quantum field theory. And here's how the hypothesis goes. The hypothesis says the vacuum energy, a kind of energy density of empty space described in quantum field theory, contributes to the cosmological constant, where the cosmological constant, as we've seen, is a kind of energy density of empty space described in general relativity. Now, one problem is that that doesn't tell you the absolute value of the cosmological constant, because we're going to think of the cosmological constant as a sum of two different things under this hypothesis. One is what we call a bare value, and that is it's a free or unknown parameter, and the other is what we're going to call a quantum corrections. Now, I don't want to dive into the details into what exactly these two terms are, how to calculate quantum corrections and quantum field theory. If you look into popular level books, you'll find various descriptions that this is something like the various ways that empty space can fluctuate or something like that. From a philosophical perspective, that's not a very good interpretation of what's going on. Then in any case, we don't need to know what this quantum corrections term really represents to see what the problem is. The problem is this. Given this hypothesis, we can estimate a natural size for these quantum corrections. And the natural size is going to be something like the fourth power of the Planck mass. The Planck mass by itself was already an absurdly large number. So the fourth power of the Planck mass is a really, really big number. And unless you had some mechanism for canceling out the difference between these two, we should then conclude that the total cosmological constant is likewise going to be some very large number, maybe on the same order of magnitude as the fourth power of the Planck mass. What we observe when we look out in the universe is that the cosmological constant is very small. It's so small that for a long time people thought it was zero. And then with the discovery of the accelerated expansion of the universe in the 1990s, people came to realize that that it's not quite zero, right? So this prediction that this particular hypothesis makes is then horrendously wrong. And how wrong is it? Well, it's wrong by 120 orders of magnitude. Now, here's a way to think about the probabilities that people want to calculate. So what we do is we take, so if we have the range of values that a parameter could have, and the hypothesis tells us that we should have a uniform distribution over that range, then we can take the total range of allowed values. In this case, it's on one side, it's 10 to the 90. Let me back a moment. So on one side is the Planck scale, on the other side is the Planck scale. This 10 to the 90 number comes along when we look at what's called the anthropic interval. So the anthropic interval is, as I said before, it's the range of values that allow life to exist. According to Barnes, one side of the anthropic interval is -10 to the -90 times this limit over here on the far left side. The other side, on the far right side, the Planck scale is going to be 10 to the -110 times larger than the right side of the anthropic interval. And then the actual observed value, which is 10 to the -120 times the natural value, is seated right here inside of the anthropic interval, as you would expect, because clearly life exists. So clearly we have to be inside the anthropic interval. And then what you do, given that uniform distribution, is you take your anthropic interval and you divide by the width, the total width. Now, if you follow that recipe, you end up with this number, 10 to the -90. So that's the probability of life given this particular physical hypothesis without postulating some sort of anthropic mechanism. That is, without postulating a deity, or that is a deity that prefers biological life forms, or maybe a multiverse or something like that. Just relative to the hypothesis I've given, what Barnes calculates is the probability is 10 to the negative 90, right? So that's an absurdly small number. It's a kind of very, very small likelihood that we needed for that first premise in the fine-tuning argument. All right, so what were the requirements for that recipe that I just gave you? Well, first was some kind of physical hypothesis. The one we discussed was that the vacuum energy from quantum field theory gravitates like a cosmological constant, so it exerts the kind of gravitational influence on the universe that a cosmological constant exhibits. We also had a probability assumption. Probability assumption here was one that assigned a uniform probability distribution over the possible different kinds of cancellations between the bare value and the quantum corrections. Or if you'd like, what this distribution is over what you're left with after you take the difference between the bare value and the quantum corrections. Those cancellations can vary then in magnitude between 0 and the fourth power of the Planck mass. Without those requirements, or ones that are at least appropriately similar, the corrected version's first premise is unjustified. So to remind you, the argument was the first premise said that the probability of the observation given theism is much, much greater than the probability of naturalism. The probability of the observation given naturalism. If we don't have the probability that is calculated, if we don't have the combination of those hypotheses, then we can't justify the claim that this probability is much, much greater than this other one. Well, what we're interested in is the probability of life given naturalism, right? That's the probability on this side of the inequality. On the right side of the inequality, the probability of the observation that is life given the hypothesis that is naturalism. And we're going to expand that out using what's called the weighted average principle. So the probability of life given naturalism and that package of hypotheses I told you about, the physical hypothesis and the probability assumption, times the probability of that package given naturalism, plus the probability of life given the naturalism and the negation of that package, times the probability of the negation of that package given naturalism. Often people will quote this first term here, probability of life given naturalism was 10 to the negative 120. As we've seen, we should really be saying 10 to the negative 90, at least according to Burns' computations. We're left with this other term, right? So if this first term is very small, then really we're left with this other term possibly being large, right? I mean, we don't know what this other term is equal to. So we don't know what the probability of life is given naturalism and the negation of that package times the probability of the negation of the package given naturalism. But unless this term is itself smaller than, say, 10 to the negative 90, the probability of life given naturalism should really be thought of as the second term. So if we say that this second term is much larger than this first term, well, we can expand this second term itself. So remember, we think about that second term, we think about P as being the combination of, here I've written as theta as a physical hypothesis, and rho, where rho is our probability assumption. What I've written out here is how to expand out that probability. We really have three possibilities, right? So if you negate this combination here, theta and rho, then you're going to have the three possibilities are that you have the negation of theta and the negation of rho, or the negation of theta and rho, or theta and the negation of rho. Technically speaking, if you negate P here, you get 4, but the fourth possibility is that it's just, well, sorry, I said that, let's back up. I made a mistake. The negation of P is just going to give you these three possibilities. All right. So if you have these three possibilities, then it's really unclear what this probability should be, right? If you don't have your physical hypothesis, then you can't apply the probability assumption. If you don't have the probability assumption, but you do have the physical hypothesis. Well, that's no good, because now you don't know whether the parameters in your physical hypothesis are probable or improbable. Right? You really need the package of both of them in order to compute those probabilities. And so we're left with that term and not knowing what it is. So is this high or low? I have no idea. Now, you could guess that maybe this isn't very high, right? After all, it seems like we had some initial motivation, at least, for thinking that that physical hypothesis was maybe right and that our probability assumption seems plausible. So maybe the negation of that package is going to be improbable. Well, what happens if we just guess that this term isn't very large? Well, now it turns out that our argument isn't valid, right? What does the first premise now turn into? Now we're no longer able to say that that this first probability is much, much greater than this other probability. Maybe this other probability isn't stupendously high, but as long as it's not like very, very low, we then can only say that this first probability is greater than this other one. And if that's all that you have, then 1 through 3 here does not entail 4. So the argument is invalid. Now, you might object that we're rejecting physical theories too quickly. I don't think that that's right. But we can look at what some people say about this. So here is a book by Donald Perkins called Particle Astrophysics. This is actually the book that I used. Well, I didn't use it, but it was the book that was assigned to me in the course that I took, where I first learned about how to calculate things involving the cosmological constant. And what it says about this issue in that book is that the mystery of dark energy is such that even the most outlandish ideas cannot be ignored. Likewise, Bianchi and Ravelli from 2010, they disagree with the physical hypothesis that we were talking about. On their view, they think that we shouldn't think that the vacuum energy from quantum field theory gravitates at all. They say that it's a mistake to identify the cosmological constant with the vacuum energy density. And then if you also look at this recent paper from Mark Schneider from 2020 called What's the Problem with the Cosmological Constant? Schneider does a really good job of unpacking some of the various possibilities here that you might have for solving the cosmological constant problem, one of which he lays out 4 different possibilities of different families of different families of approaches one could take to this issue. One member of that family says that the vacuum energy does not gravitate.
Oh, I'll just interrupt one sec, Dan.
Yes.
Carlo Ravelli, when that Bianchi and Ravelli paper came out, sometime after it, I did an interview with Carlo Ravelli, and he discusses this paper, and we had a discussion about it, which is posted on my channel, and I'll leave a link in the description.
Yeah, it's a fantastic paper, and I think they give a fairly convincing argument in that paper for thinking that maybe the vacuum energy from quantum field theory doesn't gravitate, or at least that we're not justified in thinking that it does. There also were the big zoo of less familiar proposals that I talked about before, right? When I had the slide that where I gave these in the multiverse as the more familiar proposals, there were then like 4 families of less familiar proposals. Those are also ones that are maybe worth considering. What's worth pointing out here is that these proposals don't need to be particularly probable. What we need is for their disjunction to be at least not massively improbable. And by massively improbable, we mean something like 10 to the negative 90, right? These absurdly like small numbers that people throw around when it comes to the fine-tuning argument. As long as these proposals aren't so improbable, well then we don't get the first premise that we need for the fine-tuning argument, and then the version of the fine-tuning argument that Philip gave is not logically valid. Can this be generalized? Well, yes, there's a few different ways I've thought about generalizing this. So here's a classic problem for the fine-tuning argument, is that the free parameters or physical theories cannot be made to vary over an infinite range while being assigned a uniform distribution. That's supposed to make trouble for fine-tuning arguments. So there's these 2 famous papers, one by McGrew and Bestrup, another by Coliban, Garfield, and Priest, That's Grand Priest, who's previously appeared on Philip's, on Phil's channel, on this same channel. And there's a
He's
solution.
also appeared on my channel as well, just if we're dropping references.
No, that's good. So, but it turns out that there's a solution to this normalizability problem. We saw that when we studied the cosmological constant. Remember the probability recipe that I gave? So in that recipe, we had a way of bounding the possible values of the cosmological constant using a background physical theory. When we have a background physical theory like that, so we can bound the values of the free parameters, well, then we have a uniform distribution over a finite range. And then the distribution does behave properly like a probability distribution, and we don't run into this normalization problem. Now, that's we can pull off a similar trick as we had for the cosmological constant for many of the parameters from the standard model of particle physics. In fact, for the particle masses in the Higgs Bev in particular, we can give versions of the argument that I gave before, and the Higgs Bev is a particularly nice example. That's the Higgs vacuum expectation value. We don't have to go into like the technical details here about exactly what that is, but the point that I'm making is that the argument that we set up for the cosmological constant, including in terms of things like the quantum corrections and so on, there's a quite analogous argument for these parameters describing the Higgs particle. Now, in fact, I'm not the only one saying this about the normalization problem. Earlier, I talked about Friedrichs, I don't know how to pronounce his name, but the Stanford Encyclopedia article about the fine-tuning argument. The very last section of that article discusses this kind of solution to the normalization problem. And so does Barnes. So in Barnes' 2018 paper, when he's discussing the normalization problem, his solution is precisely the same solution, at least when it comes to dimensionful parameters. So parameters that actually carry dimensions like energy or mass or something like that. Philip, oddly enough, actually mentions a quite similar solution. He keeps it a bit vague as to what exactly he's talking about, but on page 46 of his book, he gives more or less the same solution to the normalization problem. Barnes, to be fair, does make some additional arguments in that 2018 paper. So he says that there are some other parameters, something called the Yukawa couplings, this has to do with the relationship between the mass of the Higgs particle and the masses of a bunch of other particles like the electron. And he thinks that for the Yukawa couplings, because those are not dimensional parameters, you can't give this kind of solution to the normalization problem. Nonetheless, the solution that he does give for the normalization problem in that case is going to be more controversial. And so there's a kind of choice point here for the proponent of the fine-tuning argument. You can pick a parameter where we can think about it in this way, and we have the solution to the normalization problem, or we can pick a different parameter where maybe there isn't the solution to the normalization problem, or we're going to pick out a different solution to the normalization problem like Barnes advocates, but then that solution is going to be more controversial. There's still another way to generalize. It goes like this. Let's suppose that there's some theory that poorly predicts life. So according to the theory, life can exist only if the theory's free parameters or initial conditions have some improbable values. In that case, the fact that life exists might provide evidence against the theory, or at least life is going to be poorly predicted by the theory. But it doesn't necessarily provide evidence against naturalism. And importantly, in all cases where the universe has been claimed to be fine-tuned for life, it's in virtue of a fine-tuned theory. That is a theory that's fine-tuned in the physicist sense, to come back to that debate about the two senses. And why is that? Well, precisely because a parameter value consistent with life, according to that theory, is improbable. All right, well, I said a lot there, so let's chat about that.
Let me see if I'm following along enough. So the idea was that there was this extra feature to the calculation that the physicists or philosophers, or fine-tuning advocates in general, they were saying, look, the theories we've got make life seem very improbable, so finely tuned. And what you're saying is, well, there's some aspects of those theories which are required for those big numbers to come out. But those parts of those theories are very uncertain. We don't know whether those things are right or not. There's a lot of uncertainty about how you've calculated those numbers. So it's a bit like, it's like if you just think about the Bayesian picture in the first place was talking about like degrees of confidence or credence that we would have in propositions being true. And what we're using is the information that physics tells us to try and calibrate where our credences should be. They should be, like David Lewis was saying, should kind of in line with what we think the chances actually are. And where we're getting that from? Well, from physics. That's telling us how to assign the credences. But I'm thinking about the point you're making here, and tell me if this is wrong. But there's some kind of higher order uncertainty that kicks in because we're not clear. It's like I want to use the physics to tell me where to set my credences, but I'm not sure about that physics, so I'm not sure about how much it's telling me about where to put my credences. There's sort of an extra element of uncertainty, and that's over because it's not clear whether, as you were saying, stuff about like whether the background, whether the quantum vacuum energy gravitates, blah blah blah, those types of stuff. Physicists are not clear about whether those things are true or not. So that means that I can't just straightforwardly just pick the physics up and go, oh yeah, this is the right way to assign those probabilities. Like I should be unsure about that. And then that sort of gets in the way of the argument. And the end result is something like, well, I have to sort of withhold judgment or not know what the number really should be. It becomes kind of the term would be inscrutable. Right? The probability sort of just becomes impossible to state precisely. Like I just don't know enough information to say what the number is. Right? Does that seem right?
Right. I think here's something that I think is quite important and that people sometimes miss. And there was people complained about this in the comment section on the previous video. So people were making this kind of complaint. They were saying, look, isn't this based upon the physical theory that we're most confident in? Like general relativity has been very well tested. Quantum field theory has been very well tested. So isn't this like very well tested physics? Answer, no, this depends upon this particular hypothesis about how to combine the two of them. Right? It's not a hypothesis about general relativity. It's not a hypothesis about quantum field theory. It's a hypothesis at their juncture. And now it's a hypothesis that has not been well tested. And it's a hypothesis that we don't have a great deal of certainty about. But I want to add one more thing here, which is that even if suppose you did have some experiments or observation that told you that this hypothesis was right. Well, the fact that you observe life existing should break your confidence in that hypothesis. I mean, what's really important is that so when they make this claim, like that the relevant likelihood is something like 10 to the negative 90, then they're saying that there's no other contribution to that probability from the possibility that the hypothesis that you've built into what you're doing, there's no possibility that could be wrong. But let's suppose that there's like a 1% probability that the hypothesis, this background physical hypothesis that you need is incorrect. Now, 1% probability isn't very high, but it's massively higher than 10 to the negative 90. And so now the probabilities that you're comparing, it's no longer that you're comparing to 10 to the negative 90. It's now that you're comparing this hypothesis that's low but not extremely low. And this is the context in which we do actually have to say something quantitative about the priors. Right? We get away with not having to say anything about very specific about the priors, according to the fine-tuning advocate, because the likelihood of life given naturalism, they say, is so stupendously and stupidly low. But now that we've said that, hey, maybe it's something like 1% or 10%, if it's a probability of 0.1. Well, now we're no longer in the 10 to the negative 90 land. Right? So now we're in the land where we actually have to say something about priors, about other sorts of evidence, and where our total evidential situation can actually matter. Right? If you're in the land where the likelihood is 10 to the negative 90, maybe the case against naturalism is so strong that you don't even need to consider any other pieces of evidence. Like whatever you would say about, the problem of suffering, or the problem of divine hiddenness or something. You might think, oh, that can't compete at all with a number like 10 to the negative 90. But now that we have a number like 1%, 10%, these small numbers that are not stupendously or stupidly small, now we do have to think about those other kinds of considerations, and fine-tuning doesn't automatically win in favor of theism.
I wonder if there isn't a way to sort of make this more general. Like, naturalism doesn't tell us what the right theory of the cosmological constant is. It only tells us which the right theory of the only tells us what the right theory of the cosmological constant isn't. And that is, God didn't do it, basically, or there's no agent that decided what it should be. But that leaves open an enormous range of different theories of the cosmological constant. And if your theory gets it wrong by 90 orders of magnitude, then throw that theory away. It's a not very likely theory. Maybe not throw it away, but it's very unlikely. So that leaves the other theories looking better. And there are plenty of other theories, as you've said, and I can think of more. I mean, I have another video with this guy called Alejandro Perez, and he was like, oh, it's like this kind of friction term coming from quantum gravity. And again, who knows if it's right, but you're not committed as a naturalist to this theory that the fine-tuning defenders say you are. And more generally, they're basically assuming that the constants of nature under naturalism are selected at random and only once. And we don't have to assume that. There's no reason to assume that. Maybe what you're telling us with fine-tuning, if we accept the claims, is that it's not selected at random and only once, but that doesn't mean it's selected by God.
Yeah, right. So I think that this is where that weighted average principle that I showed on screen is quite important. The fact that you can break up the calculation into those different terms to represent the different possibilities. So naturalism is not going to say that the vacuum energy from quantum field theory is what's responsible for the cosmological constant. Something else is. Though, well, I shouldn't quite say it that way. So the really precise statement is that they're not going to say that statement in combination with the probability assumption, right? Because they could save that hypothesis and instead negate the probability assumption. In any case, they're not going to say that. They're not going to endorse that whole package together, because that, on their view, is a probability of 10 to the negative 90. But that other term is still going to have some contribution. And the thing that the move that theists make or at least advocates of the fine-tuning argument make with respect to the priors, is they say, oh, come on, the prior probability of theism can't be so low. It can't be unreasonable to think that it's as low as 10 to the negative 90 or something like that. So whatever you want the prior probability to be, it doesn't really matter because this likelihood is so low. Well, you can say exactly the same move, precisely the same move with the second term. Okay, maybe it's improbable that there's some other physical hypothesis. Maybe unimodular gravity is improbable. Maybe we think that. But is it 10 to the negative 90 improbable? Is it, how improbable is it really? One of the things that's sort of frustrating about it's when you read through there's this rather long paper that Luke Barnes wrote summarizing the fine-tuning argument. in response to Victor Stenger. And I do not want to defend Stenger either. But when you read through that paper, one of the things that's frustrating to me is that when Barnes considers alternatives to this particular physical hypothesis, he has various kinds of objections that he raises to them. In some cases, he wants to show that the same familiar fine-tuning problem returns for those alternative hypotheses. And if it does, fine, you just get the same problem over again. But there's other hypotheses that he describes where it's just like, okay, you have an objection to that hypothesis, so that's going to lower our credence in that hypothesis. But unless it lowers it so drastically, there's still going to be the second term in the weighted average that this alternative hypothesis will contribute to. And now I want to know, like, why should we think that it's smaller than 10 to the negative 90? Like that contribution in that weighted average. It seems to me completely unreasonable to think that that's what it would be so low. And it's unreasonable for precisely the same reason that the theist takes it to be unreasonable to set your prior so low.
And actually, I wonder if you could bring that back to like some specific hypotheses about fine-tuning more generally, not just about the cosmological constant. So, I mean, in fact, that seems to be exactly the way that Philip Goff replied to it. So I remember mentioning this theory of cosmological natural selection, where there's a sort of Darwinian process in the universe. So the universe reproduces itself, and there's a selection pressure to make more black holes, and they happen to make more stars, which gives you more life. So life just becomes a sort of happy byproduct. And if I recall correctly, Philip Goff had said, well, I've spoken to physicists about that, and they don't give it much credence. And I'm like, well, how much little credence do they give it? You know, is it 10 to the 90? You know, well, actually, for the whole, I think for all fine-tunings combined, I think Luke Barnes came up with a number of like 10 to the 136 or something. I'm like, okay, so do you want to give your credence that cosmological natural selection is right? That lower probability? You know, it seems like we can just run the same argument, right?
That's right.
And isn't it even worse than that? Because like maybe you do think that theory, my credence is 1 in 10 to the 130th power or whatever. But the point is, it would have to be the disjunction of all of the possible theories anyway. So even if there's one, which is that unlikely, you're adding it to all of the other hypotheses. So you could even shrug and say, yeah, I do think that's that unlikely. I just don't think that all of the possible theories when added together is that unlikely. So it would have to be that the sum of all of them added together is this stupidly small number, right? Isn't that right?
Yeah, so you might think it's unreasonable to think that there are 10 to the 136 possibilities, right? I mean, so if they're each like 10 to the negative 136, and you want to add them up to some reasonable value, there has to be on the order of 10 to the 136 of them, which is like a stupidly large number of hypotheses.
Why is that? If I just add 2 of them together, then that's more than it was if I just had one of them. So they don't have to add up to 1, right? They just have to be, they start approaching some kind of more tangible number.
Suppose that they add up to 0.1.
Yeah.
Right. So now you're 2 orders of magnitude.
Yeah. Right. Exactly. Okay. So fine. I'm not saying that they would be equally unlikely, but like you might just like take the hit I'm saying on that particular black hole evolution theory and say, yeah, that one's super unlikely. But next to it is a theory which is like, 1 in minus 10 to the 3 or something. And then that's such a massive chunk in comparison that I add them together, and now we're not talking about a small number anymore. I wasn't saying there'd be that many hypotheses and they were all equally unlikely. That would be...
I mean, I don't know. Like, I don't know how many hypotheses that no one's thought of yet, right? So maybe there's infinitely many hypotheses no one's thought of yet. But right, yeah. So if you had a bunch of hypotheses, suppose you had 100 hypotheses, and they're all like on the order of 1%, then each one of them contributes very little. The sum of them gets you up towards 100%. I think it's also important to realize that. So in the argument that I gave, we don't need that the probability of life given naturalism is all that high, right? I gave a version of the argument where I showed that the argument that Philip gives is invalid if we switch out the first premise for the probability of life given theism is greater than the probability of life given naturalism. So on that view, the probability of life given naturalism is lower. But the argument still doesn't succeed because the premises don't entail the conclusion.
Yeah, and if you just had the prior probabilities, like many of us do, that naturalism is just more likely intrinsically than theism, for the sorts of reasons that Phil was talking about before, that like, what do you mean a mind that's disembodied yet has causal powers, that kind of thing. If you just find that your prior probability of theism is low compared to naturalism, then that kind of contributes back in, and because that was the second premise anyway, was it the first premise establishes effectively a ratio when the evidence is considered massively favoring theism. But then there's just a ratio between the two hypotheses on their own, which might considerably favor naturalism. And what we've been talking about is ways of addressing the first ratio. And then you just come to look at the second ratio. Still, it might massively favor naturalism. And if we've done a huge job setting the first inequality back towards something like equality, then that second premise then just tilts the balance back over to naturalism again. So I think that's one way that you could. I'm not saying this fine tuning proves that naturalism is true or something, but it's just I think the sort of TLDR version of this is that like there is uncertainty about the applicability of these results from physics, and it's reasonable at the very least to say I'm not I don't buy everything that's needed in order to make these stupendously big / small, however you look at it, numbers.
Yeah.
I kind of feel like I don't know. There's something kind of vindicating about just the thought that I don't know, something about like I feel suspicious or something about people wielding such big or small numbers that it kind of equates to an unreasonable capacity on their part to be right about something to such a stupendous degree. And you just think that like, and it's also like Humean or something, where you just think like the kind of effect of like, well, maybe you're just wrong about some assumption that's buried in here. That starts to begin, maybe that's insignificant when you're talking about everyday things, but when we're pushing the kind of the limit of the numbers into these sort of stratospheric levels, where it's 1 in 10 to the minus 120 or whatever, then you only have to be slightly wrong for that number to be completely out of kilter from what's reasonable anymore. And that's why I just think like, it's like someone saying, I've figured out how to win every game of chess or something. You think like, you might think that, but there's so many different ways of playing it that like you've probably not thought about some combination of moves that doesn't, your tactic doesn't work with. In a way, it just sort of makes me think, somebody saying that, I just think, well, you're probably wrong, rather than, oh, well, I must find a way of showing that whatever. I just think, no, you're probably wrong. It's my shortcut way of just thinking, of like brushing that off. And I think that's something that's like that here. It's like somebody is misinterpreting the physics somehow if they think that these numbers are really there and that they can establish these kind of metaphysical and, dare I say it, political consequences or whatever. It just my bullshit detector's going off.
I'm wondering if you could simplify it actually and just say, if you get a result from an experiment that your theory that you think is unimaginably improbable, like the first time you run an experiment and you go, oh, look at the outcome, it's unimaginably unlikely. What's our explanation? The simplest explanation is that you're wrong, that it was unlikely.
Right.
Yeah. But one of the things that's important to point out here is that we don't need it to be the case that the probability of life given naturalism or given any particular naturalistic hypothesis is all that high, right? It could still be that life is improbable on naturalism. It's just that it's not so improbable, right? So you can still grant to the theist the premise that theism is better at predicting life than is naturalism, but the argument will still be invalid if that's all that you've granted them.
Yeah, and I think there's loads of ways where like life is does seem improbable. And, without having to think too much about physics or something, just generic stuff about like, well, what's the universe like? Most of it's uninhabitable. Only a tiny fraction of it is inhabitable. It kind of feels easy to imagine that an asteroid hit the Earth and stopped it being inhabitable. That's the sort of thing that could have happened very easily. And, on naturalism, there's nobody there protecting us with some like miraculous interventions or something. You don't have to know anything about physics. It's a generic sci-fi picture of what the world is like. You can understand how it's precarious and delicate on naturalism. You don't have to have like the exact opposite view, which is like on theism, God sort of protects us and keeps everything going like clockwork or whatever. So we must say the same thing on naturalism, that in fact life is very likely and we're secure and there's nothing could go wrong. Maybe it's all very unlikely and precarious on naturalism too.
There are stupendously improbable coincidences. I mean, not as improbable as like 10 to the negative 90, but there are improbable coincidences that really do happen. So, for instance, the fact that, at least as observed from the surface of the Earth, the angular size of the Moon is approximately the same as the angular size of the Sun, is what makes eclipses possible.
Mm-hmm.
It'd be very easy for that to have been different. For the Moon to either have, or its angular size have either been larger or smaller, and then you wouldn't have the possibility of the very nice overlap between the two of them.
But in fact, the Moon moves away from the Earth at a very slow rate, something like 1.5
So in a few hundred million
years,
I think you won't be able to see an eclipse from the Earth. But more importantly, most places on Earth can't see an eclipse. There's only quite rare places, somewhere on Earth there'll be an eclipse, total eclipse, I don't know, every year or 18 months or something like that.
Yeah, right.
But, most places don't see it. Right? It's only a very, very thin sliver that does get to see it.
But that's the case where you have these two values, the angular size of the Moon and the angular size of the Sun. And a priori, there's no reason to expect those two numbers to be the same. And you go out and you measure them and you find out that they are the same. That's a case where there's this really interesting coincidence. I don't think anyone or any serious person thinks that there's a design argument, a good design argument based upon that coincidence. But yeah, there are coincidences that happen in nature. So we don't want to say that that we should reject any theory according to which there are coincidences, right? That would be a bad theory.
And I think there are people who say that the presence of such a large moon, which is unusual for planets in this sort of range or whatever, and then the tidal effect that has, that is to do with how life may have got started, or at least some of the kind of filters that might stop life developing. It helps life kind of transition from being underwater to above water. And people, imagine a species that's confined to underwater trying to develop electronics. It just seems really hard to imagine how they would do that.
Well, fire, right?
Okay, maybe electric eels, they could do it, I guess. But,
but they still don't have fire.
Yeah, well, do they need it if they have electricity? I mean, eels could have conceivably.
I think you use fire before you get electricity. So I think you're making a really good point here. I mean, I recently read an article about the linguistic abilities of sperm whales, which are apparently much stronger than people previously thought. And so you can ask questions like, well, why is there no whale technology? I mean, I guess one possibility might be that whale language is just not sophisticated enough. Maybe it's more sophisticated than thought, but not sophisticated enough to have technology. Fine. Setting aside that possibility, she also pointed out that you can't set fires underwater, and one of the really important milestones in human technology was the ability to create fire.
That's right.
Well, written language was probably quite a big help.
Yeah, but I guess you could conceivably have written language underwater. Or like if you imagine maybe there's life in the universe and often it's confined to being on icy moons like Europa or whatever.
Yeah.
And, then there's just, it doesn't matter how great their poetry is. They're never going to be able to like get off their planet and do anything. They're just kind of stuck there where it's kind of just great luck for us. Maybe, I mean, this is just complete speculation, of course, but it might just be great luck for us that the great tidal effect of such a big moon being comparatively so close is, in fact, related to the kind of chance that we would be here having this conversation like over the internet.
But that might be different to its angular size, though, right? Because the moon might stabilize the Earth, but presumably you could do the same and have a different angular size.
So I think the thought would be that if the moon is receding from the Earth and played this important role in the development of life on Earth, then maybe there's some relationship between those parameters such that you would expect technological civilizations to appear when the moon's angular size approximates the sun's angular size or something like that. So it might, this is pure speculation, but maybe there's some like anthropic mechanism so that we sort of have to exist at the time when these things line up.
Yeah, I think there's loads of things like this. And one suspicion I have about them, though, is that like they're kind of, it's not really clear to me. Like there's a lot of speculation that goes into it. Like, it's kind of plausible maybe that we needed to climb out of the sea and get on land or whatever. And fine, that does kind of make sense. But what I don't know is the vast range of different ways that life could pop up. Like for all I know, they're not like otherwise confined to the sea. You know what I mean? Like maybe life can somehow just be completely different in ways that I can't really imagine, such that it could find a way to survive and become technological in an environment that otherwise seems completely inhospitable to me. I guess I'm saying, like, I don't know what the base rate is. And without that extra factor of knowing what the kind of range of different options might be, there's this tendency to just look at the contingent features of our own surroundings and history and go, oh, things had to be exactly like this. Otherwise life wouldn't exist, right? And like, if we didn't have a moon that exactly fits what the sun looks like in the sky. And you can think of like things that support that hypothesis, but I feel it's a bit like a sort of Just So story, you know? So you get this stuff in evolutionary development, is that what it's called? Where people speculate about like, well, early hominids must have had, you know, social structures that did blah, blah, blah. It kind of sounds like Jordan Peterson-y kind of thing. You know, there must be these hierarchies of power such that men are always in charge and the women just, you know, like to do womanly stuff, and the men are all like Chuck Norris and punching zebras in the face or whatever. And, you know, that's just working backwards from their own perspective and sort of superimposing it as some contingent feature that happens to be the case now and just supposing that must be the case in the past as well. And I don't know whether that's a fair thing to say about what's going on in the fine-tuning case, but there's some similarity between that.
I mean, I'm wondering the way people often reply to an argument like that is like, okay, yeah, you could imagine there might be silicon life rather than carbon life, but you can't imagine life without atoms. You know, we can't imagine life made out of dark matter because dark matter doesn't interact in a way that you could possibly give you the complexity of life. But my reply to that would be, say, well, let's just suppose I said, look, there is some other kind of life that would be possible with the other constants, but I can't really give you a description of how it works or what it would do. And you'd probably say, yeah, that's kind of lame because, you know, you just pulled it out of a hat and you haven't given me anything concrete about how that life could exist if it's just made of dark matter. But I want to say the same to the theists. I'm like, well, all the minds that I can imagine are attached to bodies. Even if you think dualism is true, whenever a mind does design work, it's always attached to a body. So I can't imagine any mind that can exist without a body and can exist, you know, at the early universe when the temperature was, you know, God knows what, some ludicrously high number. There's no minds that I can imagine that can exist in that kind of thing. Give me details. How does this mind work? And sure enough, they're going to have exactly the same reply that I would have if I tried to imagine, you know, life made out of dark matter. So it seems like there's actually, to me, they're a bit more symmetrical the way you would reply to these kinds of arguments, because the very basis they want to say life can't exist with different constants is the same basis I want to say mind can't exist with different, you know, in the early universe, or, you know, that's where it has to be for them to get the fine-tuning argument to work. I mean, what do you think, Dan? Is there some similarity there?
Yeah, and I think this goes particularly nicely with what I was saying about how we might have to end up modifying the first premise of the corrected argument, right? When we switch to the greater sign to the greater than sign, now the prior probabilities are much more important than they were previously. And in this case, these kinds of considerations, like what is our empirical experience with minds like, is going to play a role, because we have to use the principle of total evidence tells us that we need to take into account all of the evidence that we have and not just some portion of it.
All right. Well, Dan, thank you so much for presenting these slides. They've been absolutely brilliant. It's super insightful. And if you have any thoughts on this, do leave them in the comments. If you have suggestions for future shows, leave those too. And if you like this content, like and subscribe. And we will see you next time on the SciPhi Show.